This is a charge, or to be more specific, a negative charge, which we call an electron. An interesting characteristic about charges is that they have something called an electric field, as demonstrated with these lines. This idea will become very important later on. For demonstrative purposes, let's assume this electron is in a vacuum-like space. Suppose we oscillate this charge in the y direction and we propagate it rectilinearly with velocity v. The motion of an oscillating charge can be modeled as a sine function as it progresses with a velocity through time. Remember what I said about charges having an electric field? Well, let's have a look at what Maxwell said and why that's important. Let's move the charge downwards a quarter of a revolution. Because the position of the electric charge changes, we've created a changing electric field. Remember, the electric field goes with the charge, so this only makes sense. Let's move it up again by 1/4 of a whole revolution. Again, we have a changing electric field. But didn't Maxwell say something about a magnetic field? Yep, he said that a changing electric field would give rise to a magnetic field, which is what you can see with this diagram. So what about the magnetic field? Surely that has something to do with the propagation of electromagnetic waves. And it sure does. About 50 years earlier, another nerd came along called Michael Faraday with his law of induction, which stated that a changing magnetic field would give rise to an EMF which would cause a charge to move. With the basic features covered, we've also got some other cooler features to talk about. Because electromagnetic waves self-propagate, they can theoretically travel forever. So if you have Johnny on one side of the universe who shoots an electromagnetic wave, Jane will theoretically receive it because electromagnetic waves never run out of energy. Also, electromagnetic waves are really fast. Back when Maxwell proposed the existence of electromagnetic waves, he used this formula to prove that electromagnetic waves travel at the speed of light. They also don't require a medium to propagate, so if you put one in space or on Earth, they will still propagate because they can self-propagate. Another feature of an electromagnetic wave is that its frequency and wavelength can vary depending on how fast we oscillate the particle. So if we begin to move this particle really quickly, we'll see that the frequency increases, which is characterized by a decrease in the wavelength. Since the magnetic field is unified to the electric field, we'll also see the same effect. Okay, cool. So we've got this weird wave, but what are the implications for light? Well, for the wave model, light is just a type of radiation which exists on a spectrum called the electromagnetic spectrum. If our electromagnetic wave has large wavelengths, then we'll get radio waves. But if we decrease our wavelength, we'll get gamma rays. Note that if our wavelength decreases, we'll have an increase in energy, which is why gamma rays are so dangerous. But if we go somewhere in the center, we'll get something called visible light. So if we get a single electromagnetic wave, and let's say we propagate it at a wavelength of red light, then as you can see, we will get red light. But if we decrease the wavelength of our wave, we will get a color like violet.